Hi, in this video I'm going to continue our look into this chain of RGB LEDs. As established in the previous video, there's actually a little bit of communication and clever trickery going on here, so that each of the LEDs has a red, green and blue command as well as an address, allowing us to have this fade pattern for something more complex than a single colour, which could be achieved with reverse polarity and a simple circuit like an H-bridge. In the previous video I skimmed over a couple of details and I'd like to cover some of that now. But let me just let you know that I think I've tracked down the company that sells this in the UK at least, and I've sent them an email just in case they felt like being helpful and responding with what the LED is. I have also had a bit more of a look on distributors like DigiKey to try and identify what this LED might be, but I couldn't find any good information. Now, as established previously, these LEDs have a red, green, blue control as well as an address system, which allows us to identify two independent chains of all of the odd LEDs and then all of the even LEDs, and individually control their colour and brightness. If we hook this back up to the scope, then we can have a bit more of a look into what's actually going on and try and understand how the PWM is being implemented. So if we remove the cap again, and then hook up to that wire that we were using previously. I've re-enabled the AC coupling and adjusted the time base so that we can see a couple of cycles on the display at once. If we take a single capture halfway through and start to dig into what's actually going on, then we can hopefully get a better understanding. In the previous video we theorised that possibly when the high signal is actually at this lower level, that maybe the odd and even sets of LEDs were on. In this intermediate stage then perhaps the odd or even were on, and at this top level then perhaps none of the LEDs are on. If we adjust the horizontal position and zoom in, then at this point we'd expect to see two commands coming through, turning both the odd and even pairs on, and sure enough, here it is. So what we see here is that we're using the LEDs configured for this purple, and we can immediately see now that both the address 1 and address 2 LEDs are being configured for purple. This is by using the 101 in the blue, green, red fields, and address 1 here and address 2 here in binary. So that confirms that from this point into this low region here, we have both pairs of LEDs on. In this area we'd now like to confirm our suspicions that we only have one of the sets of LEDs on. So again, if we scroll across and then zoom in, we can try to identify what's actually happening. And here we can immediately see that LEDs with address 1 are being turned off. Again, to confirm that after this point none of the LEDs are on, we can see that LEDs with address 2 are now being turned off. So if we put that together, we can start to write onto or assign values onto this waveform here. And we were quite correct in expecting that the low signal here was all of the LEDs on, providing an extra drain through that resistor. The middle has one set of LEDs and the top has only or no LEDs turned on. Now, using that we can draw the waveform on top, and I'll try and do that after the video. And if we then press run again, we can start to see that the PWM is being controlled using this method. Now, as we've identified, the start of the cycle is actually the beginning of the low period, and we're not triggering off that very reliably. So I'd like to try something now, using a photodiode to actually hold up against the LEDs and provide us with a nice digital signal which would hopefully give us the start of the period on the display. I don't actually have a photodiode to hand, but I do have this LED of unknown colour and origin. Obviously, forward biasing it we should get some light out, but reverse biasing it I believe we should be able to get it to react to light fed into the front. And I have a 1K resistor. So I'm just going to put this together on a breadboard and see what we can get out. I've set the power supply for 3.3 volts at 200 milliamps, and if we hook up the power, then we should hopefully get the LED to light up. There we go. Believe it or not, it's a flashing green LED, so I'm going to need to go digging for another one. Flashing blue. Flashing yellow. Flashing blue again. This is why you try not to have a bag of miscellaneous LEDs. Where have all these flashing LEDs come from? Okay, I've just been through this entire bag of miscellaneous LEDs, and the best one I've located was this clear red LED. Unfortunately, even that's not good enough. If I reverse bias it and then show you the scope screen while I flash this really bright torch at it, you'll see what I mean by not having enough of a signal to work with, especially given that we're trying to see this LED, not this LED. As you can see, we're right down in the noise here. We've got 50 millivolts per division, and if I take that really bright LED torch I was showing you just now and bring it over and then far away, you can see that we get a bit of a spike. There you go. That is unfortunately nowhere near enough of a signal. If I was now to shine the LED chain at it, you can see what it looks like. Just nothing at all. Okay, I pointed the LED chain at the red LED, which is now reverse biased against a 220k resistor, and we can see the PWM coming through. Look at that. I'm going to try a slightly larger resistor again and see if we get an even better signal. Hopefully we'll have something clean enough to trigger off. At 1 mega ohm we're starting to get the 50 Hertz through, which is a little bit frustrating, but we'll have to see how this goes. What are we going for? Edge, line, there. 50 Hertz. Now if I bring the LEDs close again, then what does that do? Oh, perfect, look at that. Just a quick look at the breadboard and the circuit I'm using to catch the light output from the chain and trigger the oscilloscope. I found a nice clear red LED in my bag of miscellaneous LEDs, and it's currently wired up across a 3.3 volt power supply with a 1 kilo ohm resistor. Now, to make this LED work as a light sensor rather than a light emitter, we have to reverse bias it. That's simple enough, and of course it prevents the LED from lighting up. Now, if I was to bring the chain close, then we don't have nearly enough sensitivity to see the output of the chain. I was originally using this very bright torch to try to test the signal, and it did see something, but it was a very small signal, about 40 millivolts or so. So what I did is I swapped out the 1 kilo ohm resistor for a 1 mega ohm resistor, and that provides a very, very big signal when using the bright torch. It's very easy to see, very clear. It also means that now when we use a much dimmer light source like the LED chain, we actually get a good signal out of it. So now if we look at 200 millivolts per division, there we have it. So now we can use this is the last LED in the chain, we can use this to start triggering. There you go, look at that. Now if we bring channel 1 back into play, then we should hopefully see some expected results. There we go, look at that. Now that we're triggering on the LED's output rather than the burst of data on the power line, we can really see how the PWM is implemented, and you can see that if I talk you through it, we've got 0% here, about 50, and then 100%, back down to 50 and 0 again. The other LED in the chain will have the 180 degree out of phase with that. So if we take a single capture of about 50% duty cycle and come right in, then you can see here that the LED is powering up while the voltage is high, and then it turns off while the voltage is low. The curves on this trace are just because of how I'm capturing the light output of the LED. I've turned the trigger back to follow the yellow trace, and I just want to talk through the transitions that we're looking at on here. Now, it could be that this is a higher level PWM to current limit the LEDs, but I suspect that it might be clock related. All digital electronics require a clock so that they can have a good reference for time passing and advancing from state to state. And here I suspect that the micro that's in the bung is providing that clock through the power line along with the data. So this clock remains stable, and it's only interrupted during these brief periods where there's data on the line. That's something that I think we're going to have to re-implement when we do this ourselves, but we can have a play and we can try providing no clock or a clock and see if it works without. I think that nicely covers the topics I skipped over in the previous video, so let's try and implement our own controller for this chain of LEDs. Welcome to the computer. I'm just going to quickly draw out the schematic for the circuit that I want to lay out on the breadboard. Believe it or not, something that I always have to look up is how to use a transistor as a switch. So on SparkFun here we have a good tutorial about transistors and how to use them as switches. We want to pull up to the supply rail, which means that we need to use a PNP transistor as outlined here. So on this schematic diagram we need a PNP transistor, we need a resistor, a base resistor as well, and two diodes. We should also have a DC supply as well. The DC supply will be provided by our dev board, and it's a 3.3 volt supply. The base resistor we will use a 1K resistor for, and this resistor on the original board is about 30 ohms, but I think we're going to use 47 ohms. These two signal diodes will provide us with the voltage drop we need. The LED chain will be connected between these 2 points, and the micro will have influence over this line to control the transistor. The transistor will pull the LED chain supply rail up to our 3.3 volt rail, and these two diodes will provide a approximately 0.7 volt drop each, so a 1.4 volt drop between the both of them. That will give us the high-high and the high-low supply voltage. I've implemented the circuit I showed you on the screen just now. We've got the two signal diodes providing a 0.7 volt drop each, giving a total of 1.4 volts. And then round the back here we have a PNP transistor which we can use to pull the supply to the LED chain up through a 47 ohm resistor, adjusted from the 30 ohm I showed you on the screen. Then of course there's the 1K base resistor as well. To make sure that this works as intended, it's always a good idea. We can make use of a clear red LED, which you may notice from its previous starring role, and a 1 kilo ohm resistor. Now, when I bring this wire to 0 volts, that LED should become brighter because it's being pulled up. Instead of the fixed 1.4 volt drop, it should have a negligible drop across the transistor and then the 47 ohm resistor instead. And sure enough, when you touch, it does get brighter. Now, to check the voltages and things, we can hook that up to the scope. So I'm just going to take the LED's positive and the 0 volt rail, and that should see the same voltage that our LED chain will get. That green wire is currently floating, and as you can see, the LED chain would currently be supplied by 2 volts. If I bring that floating wire now to ground, there's a step up to approximately 3 volts, which should give us the ability to communicate with the LED chain, no problem. Now if we pulse that in just the right way, we should be able to control the chain, and so that's what we're going to do now with micro. Now to change this circuit slightly for the LED chain and the micro we're going to use, we need to obviously pull off the red LED and its limiting resistor, and we can get rid of the bench power supply as we're going to use the power provided by the dev board. The dev board we're going to drive the chain is one of these generic blue pill boards. It has an STM32F103 on board, and though there aren't any specific peripherals which will work directly with the chain, we might in the long run be able to coerce some timers and some DMA operations to make it work nicely. It also has a USB interface, which means that we could potentially control the chain from a computer, which is one of the long-term goals. I'm going to wire up the dev board to the circuit we've laid out on the breadboard here. The dev board provides us with 3.3 volts, which means we can just use that supply to run the LED chain. And then, because we only intend to bit bang the signal to begin with, we can use any standard GPIO pin for the base of that transistor. So I'm going to go for B9, as that's nice and close to the other signals. I'm also going to use one of these generic ST-Link modules, which can be purchased on eBay or similar very cheaply. I'm not going to cover full getting started on this board, but I will write out some code and walk you through that. One other final step we need to take, of course, is to remove the LED chain from the existing control board. It's obviously very important to keep track of which of these is the positive wire, so I'm going to connect the positive to a green solid core wire, which we can use to plug into the breadboard as well. And then the negative wire just goes into a black solid core wire. There we are, slide them out one by one. And then, just to keep things clean and prevent shorts and things, we're going to put some heat shrink over the joints. And then finally, to bring this full circle, we connect the black wire from the LED chain to the 0-volt rail and the green wire to the diodes and transistor. And now we go and sit on the computer and try and make it work. I'm just going to use a piece of wire here to keep the chain under control. I'm going to leave it here for this video, but in the next we'll look at writing the software and getting the chain operational under our control.